then therefore, a series capacitor provides for a voltage rise which increases automatically and instantaneously as the load grows, right. So, that means if load increases, current I will increases. So, that I is varying actually. So, QC also will varying, that is why it is analogous to some extent, that is we call it is analogous to voltage regulator, right. So, also a series capacitor produces more net voltage rise than a shunt capacitor at lower power factor, naturally, because it is a series capacitor is basically compensating the voltage drop. So, your what you call that your voltage improvement using series capacitor is much higher, and though not much, in the shunt capacitor also improve the voltage level, but not like the series capacitor, right. So, however, a series capacitor betters the system power factor much less than a shunt capacitor and has little effect on the source current. So, series capacitor actually has no effect on the source current, right, and it does not improve much to the power factor, only there is a reduction in power loss because of the voltage improvement, right. So, consider the feeder circuit and its voltage phasor diagram, and so this is this we have seen figure 1a and c, right, and this is the voltage drop through the feeder can be this we have got. So, we have seen this diagram. From this diagram we have already shown you that I have made it all these things from this diagram. From this diagram the voltage drop actually we have seen it is IR cos theta plus IXL sin theta when series capacitor was not there, right. So, it is equation 1. Similarly, this all the nomenclature is given, right. Similarly, when for the other part we have also seen the voltage drop approximately is equal to IR cos theta plus IXL minus XC, this is equation 2, right, where XC is equal to capacitive reactance of the series capacitor. So, this already we have seen. Now, next is the overcompensation. So, usually the series capacitor size is selected for a distribution feeder application in such a way that the resultant capacitive reactance is smaller than the inductive reactance of the feeder circuit. So, if it is overcompensation at the receiving end voltage at normal load and at the start of a large motor, right. If it is this is the current I lagging current, right. If it is overcompensation, right, that means your that is XL minus XC is actually becoming negative, right. If it is overcompensated, so it is the IR will be there. So, earlier if it is as long as XL less than XC, phasor diagram was this side because XL less than XC from this diagram, but if XL greater than XC then it is negative, it will move to this side. That is why this phasor diagram I XL minus XC is to this side, right. So, and this is your V, this angle is never 90 degree, right, it cannot be unless and until some special case, but because of my drawing, right. But this angle is theta and this is your sending end voltage for the overcompensation cases. Now, particularly and second thing is this phasor diagram at the start of a larger motor, right. So, however, in certain application where the resistance of the feeder circuit is larger than that is inductive reactance, right, the reverse might prefer, so that the resultant voltage drop will be IR cos theta minus I XC minus XL sin theta, right, because at the start of you perhaps you know that your reverse might be preferred in certain application, right. So, in that case suppose it is overcompensated. So, in that case the voltage drop will be IR cos theta minus I XC minus XL sin theta, that means there will be heavy voltage drop because of this minus sign here, right, and in that and XC greater than XL, remember XC greater than XL. So, the resultant condition is known as overcompensation, right. So, figure 2a shows a voltage phasor diagram for overcompensation at normal load. This is at the normal load, this is overcompensation case, right. Whereas, your what you call at times when the selected level of overcompensation strictly based on normal load, the resultant compensation of the receiving end voltage may not be pleasing at all, because the lagging current your this current is lagging, this current is lagging because of the lagging current of a large motor start, because you know the motor starting current may be 2.5 to 3 times then is rated current from electrical machines, you have studied that, right, and extraordinarily large voltage rise as shown in figure 2b, right, this is figure 2b. So, in that case, right, which is especially harmful to the lights, shortening the lives and causes light flicker resulting in consumer complaints, right. So, this consideration these are certain consideration you have to your what you call you have to consider this, because of the large current this IR voltage drop is higher, that is why compared to this this on the, it is not on the scale, but this IR and IXL minus XC will be higher. So, one has to be very cautious about series capacitor, right. So, this is certain drawback of the series capacitor, right. Then leading power factor case. So, when power factor is leading, when power factor, this is your current phasor and this is your, this is VR, I forgot to mention this is VR, right, and this is your IR, because current is leading. So, IR, IXL, and this is never 90 degree, right, because of my drawing it shows like this, but not, right, it may be anything. So, and this is the your what you call that your leading power factor case. In that case, there is a possibility that Vs may be it depends on the current and line parameters, Vs may be less than or greater than Vr also, either way it is true. Vr also may be greater than Vs or less than Vs, either way it is true. So, this is voltage diagram when the current is leading, right, and this is when compensation is there. Suppose leading current condition, the compensation is there. So, this is IXL, some part is compensated IXC, right, and in that case this is your Vs dash, this is Vr, this is IR, and this angle is theta. So, whenever you use series capacitor, this angle is not changed actually, right, almost same, but due to the series compensation the voltage Vs dash has changed. So, because of that, although it is showing Vr also, when you compute Vr, due to that Vr also will be different, right. So, it is not, these two are not same, right. So, that means the load current, your what you call, something I have written here for you, something I have explained only, right. Therefore, that to decrease the voltage drop considerably between the sending end and receiving ends by the application of a series capacitor, right, the load current must have a lagging power factor, right. Lagging power factor is preferable, right. As an example, figure 3a shows a I showed you all this figure and explain also voltage diagram with a leading load power factor without having series capacitor in the line, and figure 3b also I showed you, right, the resultant phasor diagram with the same leading load power factor, but this time with series capacitor in the line, right. So, as can be seen from figure 3b, just this figure I showed you, just this figure, this figure, this is figure 3b, this is figure 3b, right. So, if you assume that unity power factor case, say cos theta is equal to 1, that is unity power factor case, then I and V are in the same, they are in same phase, Vr and I, if theta is 0, right. In that case, that sin theta is approximately 0, and therefore, I into XL minus XC sin theta is equal to 0, right. In that case, what will happen, that this term actually is becoming 0, I into this term is becoming 0 in equation 3. So, in that case, what will happen, that your Vd voltage drop will be simply I into R, right, because that term second term is vanished. So, this is thus in such application series capacitors practically have no value, because your Xc is equal to your XL and your Vd that sorry unity power factor case, right, not Xc is equal to XL, that unity power factor case voltage drop is simply IR. So, series capacitor it has no value, right. So, because of the aforementioned reasons and others, for example, ferro resonance in transformers, subsynchronous resonance is the more pronounced, right, during motor starting of motors during normal operation, and difficulty in protection of capacitors, series capacitors of course, from system fault current. Series capacitors do not have large application in distribution system. So, there is not much application for the series capacitor in the distribution system, right. So, these are the certain things about the series capacitor, and after that we will go for your what you call the shunt capacitor, right. So, next is your what you call the shunt capacitor. So, in the case of shunt capacitor case, this is the diagram without your what you call without shunt capacitor. Impedance is Z is equal to R plus JXL and Z is equal to here R plus JXL, but at the receiving end say a shunt capacitor is connected, current is IC and its reactance is XC, and this is the same phasor diagram as in the case of without anything, right. So, current is lagging we have taken, current is lagging we have taken, all the write up it is here, but I am explaining that, right. And this is your what you call that your that is your phasor, this phasor diagram corresponding to this, and this phasor diagram corresponding to this. It is actually capacitor, it draws leading current, and this voltage I have missed it, this is actually VR, this voltage is VR, and leading current it is IC, right, it is IC. This angle is 90 degree, and because of that, right, suppose this angle is delta dash, because as you have your what you call, from this diagram you can make out the current here I dash is equal to IC plus the I current which is going to the load, this is at the receiving end side, right. So, this is your I dash R, because here it is I dash into R this side, right, plus I dash XL, this one I dash XL, right, and this is in this case your this current is IC. So, this current is I, that is this current without any capacitor. Now, capacitor, because this IC current, it is your what you call, it is making 90 degree angle with this one. So, phasor from this side it will move like this. So, this is IC. So, finally, it is coming to I dash, right. So, because your I dash is equal to I dash is equal to I plus IC. So, if you come to there, I dash is equal to I plus IC, right. Here if you apply Kirchhoff's first law here, I dash will be your I plus IC. If you look at this phasor diagram, that I is equal to your I dash is equal to I dash is equal to I plus IC. So, that means this effective that current magnitude I dash current actually is decreasing, current is decreasing. That means, here power factor angle was theta, now it is theta dash because of series capacitor. That means, theta dash is getting decreased, that means power factor actually is improved, right. Therefore, this is your I dash R, this is I dash XL, and this is I dash J. So, voltage drop, right. So, that is why if you put shunt capacitor, that your what you call that it improves the power factor, whereas series capacitor actually there is no change of theta, but in the case of shunt capacitor there is a change of theta, right. So, if current that means current decreases means the loss I square R without your this thing what you call, this is actually your what you call I, sorry, not IS, right. So, here it was current I, so it was I square R. So, I is magnitude of I was greater than this one. So, power loss is high, but here from this diagram you can make out I dash, if you take its magnitude I dash actually compared to this I is decreasing. So, here power loss will be magnitude I dash square into R. So, power loss will decrease. So, main purpose of the series capacitor is to reduce the power loss in the network, shunt capacitor, right, main purpose of the shunt capacitor. So, that is why this is the phasor diagram. Hope this is understandable, right. So, all these things write up is here. So, in a sense, shunt capacitor modify the characteristic of an inductive load by drawing a leading current, everything I told you, right, everything I have written here also, which counteract some of all of the lagging component of the inductive load current at the point of installation, right. So, actually if you look at the diagram, this I dash, this capacitor is connected, right. So, as this it is drawing leading current. So, it is actually compensating some of the reactive load at the your what you call at the receiving end. So, therefore, a shunt capacitor has the same effect as an overexcited synchronous condenser, generator or motor, right, effect is similar. But as shown in figure 4, by the application of shunt capacitor to a feeder, the magnitude of the source current can be reduced. I told you that this is the source current, this magnitude of the source current actually is reduced, this is I dash now. If you look at the phasor diagram, this I dash is less than I, right, and the power factor can be improved, because earlier that angle was higher, now angle is decreased. So, naturally cos theta will increase, right, cos theta dash rather will increase, right, and the power factor can, and consequently the voltage drop between the sending and receiving a load is also reduced, because of your what you call, because of this capacitor the voltage drop will also reduce, because this current actually getting decreased. So, I dash into R plus JXL will decrease. Therefore, at this point, if you this point remains same. So, at this point voltage also will improve, receiving end voltage will improve, though not much, but it will improve, right. So, however, shunt capacitor do not affect current or power factor beyond their point of application. This I have explained your previously in that your what you call in that your previous class, that wherever your capacitor is connected and beyond that point it will not be affected, only little bit effect will be there due to the improvement of the voltage, right. And figure 4 and AC show the single line diagram of line and this is voltage phasor diagram, and before the addition of the shunt capacitor, and figure 4 B and D show them after the this thing. I mean this one, this is figure 4, this is A and C, this is B and D, all I have explained, right. So, voltage drop in feeders or in the short lines with lagging power factor can be approximated at IR into R into IX into XL. That why we are writing this, that we have seen no, that voltage drop is equal to IR cos theta plus IX sin theta. Actually, it is actually I cos theta into R, that is your and this one is, that is x axis component, and I sin it is XL, right, it is XL, I sin theta into XL, right. This is actually x component. So, we can write this is Ix into R and this is y axis component, this is we can make Iy into XL, right. So, but anyway, this is what this is what I am writing this one, instead of this real component, instead of x component, x axis component, what I am writing, this is IR into R, that is your resistive that is that R into R, that drop related to the resistive part. So, IR into R as it is related to reactance part. So, instead of Y I am writing Ix into XL, right, this way I am writing. So, here your voltage drop, that is why this equation from this only we are writing that it is IR, that is the real part, your resistive part voltage drop IR into R, and this is the inductive part, that is why Ix into XL. Actually, this is your x axis component and this Ix is y axis component of the current. So, this is equation 5, right, but for easy remembering IR into R plus Ix into XL, right, where IR is equal to I cos theta and Ix is equal to I sin theta, right. So, R is the total resistance of the feeder, that is in ohm, XL is equal to total inductive reactance of the feeder, it is in ohm. So, IR is equal to real component of current in ampere and Ix is equal to reactive component of current lagging the voltage by 90 degree, it is ampere, right. When a capacitor is installed at the receiving end line as shown in figure B, the resultant voltage drop can be calculated approximately. This is very simple, it will be Vd is equal to IR into IR, you know everything now, plus Ix into XL minus Ic into XL, that is this figure. Several times I have told, from this figure also you can write that Vs dash cosine delta dash is equal to your I dash R, right, your what you call cos theta and I dash XL sin theta. So, and of course, your what you call minus your ICXL will come, because this capacitive current is there, because I dash is equal to basically it is I plus your what you call I dash is equal to I plus IC, right. So, because of this just everything I have told, this I dash, if you take this I dash XL, actually I dash is equal to your I plus your what you call IC, right. So, in that case, if you just little bit if you simplify of your own, you will see that voltage drop will be IR into R plus Ix into XL minus IC into XL, right. This is actually equation 6, where IC is the reactive component of current leading the voltage by 90 degree, right. So, whenever you consider IC in this phasor diagram simplification, please see that current is leading, that means that angle has to be considered by 90 degree, right. So, in that case, your difference between the voltage drop calculated by using equation 5 and 6, that is basically the voltage rise will be IC into XL, because if this much voltage, I mean voltage drop, this much is less means this much actually voltage rise, right. In other way, voltage drop is less means this voltage, this much is the IC into XL is the voltage rise, right. So, therefore, your power factor curve, this is your I cos theta, this is Ix sin theta, this is actually I, and this is power triangle, this is P and this is Q, this is equation 7, right. Therefore, this is phasor diagram and this is your power triangle. That means, I mean that means that in that capacitor application I was telling you something. Suppose if you take for example, suppose this is your sending end node and this is your receiving end node, right, and you have a load, suppose it is PL plus JQL, and same diagram we have taken. Suppose you have connected capacitor, this is say JQC and this is your sending end node, this is your receiving end node. this line has impedance r plus jx, this line has impedance r plus jx, right. Because of this, that initially, I mean, suppose current was, suppose it is a lagging current, for example, it is a lagging current. For your understanding, suppose the current is I is equal to say I d minus j I or I q, right. Previously, while explaining, I took I d plus j I q. This is for simply, that is just for purpose of understanding, that because of the lagging current we can take I d minus j I q, right. So, this current is flowing this direction, this I is flowing this direction, but because of this capacitor, no, this capacitor from the connecting node to the source, the current flows. So, this way that current will flow, because current is leading, this way it will flow. That means, as soon as you would put the capacitor, that your this current, say without capacitor, shunt capacitor, when the shunt capacitor was not there, without shunt capacitor. But as you put it here, then I dash actually will be I d minus j I q minus I c, because it is that means this much of reduction, right. So, this is actually, that means this is actually I d minus j I q, right, plus your j I c, this way we can write. So, in actually this part is getting decreased, but this part almost not change, but because of the voltage improvement there will be, if you go through computer simulation you will find there will be slight change, but for the our understanding, say this part remain constant, this part also remain constant with capacitor also. So, because of this part is decreasing, that means before that, look, before that power loss was R into I square, right. That means R into I d square plus I q square, right, because modulus of this is your root over I d square plus I q square, therefore, it is I d square plus I q square. As soon as you put the capacitor this part, the loss will be actually in the bracket I can write I d square plus I q minus I c square, right, because this part is getting decreased, right, this part is getting decreased. That is why power loss will reduce, but listen one thing, that theoretically you can make I q is equal to I c, that means this part will be 0. That means, R into I d square, this loss will remain in the circuit, that is the inherent property of any circuit, common circuit, right. That means, you cannot make power loss in a network completely 0, it is impossible, right. So, just taking a simple example, I want to show that this part that is your, if you take mod of I, it is root over I d square plus I q square. If you take this one without capacitor, if you put capacitor, it is R into I d square plus I q minus I c square. But theoretically you can make I q is equal to I c. If you make I q greater than I c, does not matter, it is square, some component will be added here, but ideal condition I q is equal to I c means this term will vanish. That means, if it is so, then its loss will be R I d square. That means, loss in any network cannot be made to 0. This part of the power loss will remain in any electrical circuit, that is the inherent property of any circuit, you cannot make it to 0. Sometimes book may not be given, but sometimes after reading research article I have found that this loss actually can be made it I d square plus R I q square. This is R I d square, this is R I q square. This sometimes we can call, this is the direct axis component of the power loss, and this is your quadrature axis component of the power loss. So, theoretically this quadrature axis component, it can be made it to 0, right, because of I q is equal to I c. Say it is possible, but this you cannot touch, right, it will remain in the circuit, right. So, unless until your load is 0, this I d cannot be 0, right. So, anyway, that is not the case. So, this R I d square will remain in the circuit, any this cannot minimize, this will be the, I mean theoretically that R I d square actually minimum power loss in the network. I hope you have understood this, right. This is very interesting, but I thought I should tell you, right. So, this is actually your what you call that your, that is that voltage, I mean as far as voltage drop reduction is there. So, this much actually the voltage rise, right, and this is your power triangle, and angle of course is theta, right. So, now suppose you have, this is your sending end and this is your receiving end, right, and your this is your what you call that shunt capacitor is connected, Q C J I have not shown here every time, but understandable, and this is the Q load, right. Now, without capacitor, when this is not there, if you draw the power triangle, so this is this theta 1 actually is the angle without using shunt capacitor, right, without using shunt capacitor. So, at that time that when it is not there, right, if it is not there, then at that time Q is equal to QL, right. So, in that case your assuming that there is no loss in the network, assuming that there is no loss in the network. So, this is your P and this is your what you call that Q is equal to QL, this is actually QL, this from here to here it is QL, right. So, in and suppose if for the sake of thing that suppose this is your point O say, right, and this is say point A, right. So, at that time this when some capacitor is not there, it is Q is equal to QL. So, in that case angle is theta 1, that is without shunt capacitor, loss is neglected, loss is not there. Now, suppose this QC is connected, that means as soon as this QC is connected, that means from the connecting node, from this node, that actually that capacitive current will flow from the connecting node toward the source. This is actually source, right, this is actually source. So, that means effective Q which will come from the grid or from the source, this side is source, right, it will be QL minus QC. So, in that case your what you call, that means it will draw less reactive power from the source or from the grid, because this QC actually as it is drawing less means actually effectively that your what you call that load reactive power is getting compensated, basically it will become QL minus QC. So, that is why in the second it is S1 is the apparent power, initially that I will show you, initially S1 is equal to, when nothing is there, it is equal to P square plus Q square, when your Q or QL square rather, right. But as soon as you put some amount of capacitor QC, right. So, at that time Q will be QL minus QC. So, this height say it is A, B, C, say this is B, right. Then at that time PB will be Q is equal to QL minus QC. That means your apparent power drawing from the substation or drawing from the source, right, will decrease. S2 will be at that time P plus root over your QL minus QC square. That means because this QC is coming from the shunt capacitor, all the total is QL, right, without considering any loss, and this is the power triangle. Now, this is the simple thing, right. Power actually loss is not considered here, just for the purpose of understanding, but just I showed you all the losses. Same thing, this diagram is same. If loss is there, then I told you what is the your what you call, what is the your effect, right. So, in that case assume that a load is supplied with a real power P. So, this load has a real power P and reactive load is QL. So, it is P plus JQL without any capacitor, shunt capacitor, right, and lagging power factor is QL and apparent power is S1, right, and at a lagging power factor. So, cos theta 1 from this from this triangle actually cos theta 1 will be basically OP upon your OA, that is your P upon S1, P upon S1, that is P upon root over P square plus QL square, right, because without anything the load was P plus JQL. So, it will be root over P square plus QL square, that is P square plus QL square to the power half. This is actually equation 8, right. Now, when a shunt capacitor, suppose QC kilowatt is installed at the load, suppose capacitor is installed at the load, the power factor can be improved from cos theta 1 to cos theta 2, because angle getting decreased. So, cos theta will increase. So, this is cos theta 2, in that case cos theta 2 will be OP upon your OB, right. So, it is actually that means P upon S2, that is P, this OP is P and this is OB is S2. So, P upon S2. So, basically it is P upon root over P square plus Q, that is P square plus Q square to the power half, right. So, Q is equal to actually this one QL minus QC, this much is drawing from the your source. Therefore, it will be earlier Q is equal to QL, earlier Q is equal to QL, that is why you wrote P square plus QL square, because when your what you call when QC was not there, it was 0, Q was equal to QL. So, not writing again and again, directly written P square plus QL square to the power half, right. Yeah. Now, when it is there, the cos theta will be P upon S2. So, P upon P square plus Q square to the power half, that is under root of that, right, or cos theta will be P upon P square plus QL minus Q square to the half, right. So, that means whenever you put shunt capacitor, right, it actually absorb the your what you call it reduce the reactive power drawn from the source. So, such that it improves the power factor of the your what you call that if it is a substation, then it will improve the power factor of substation. At the same time that you will find that load is there. So, for example, in industry all the induction motor load, you will find the shunt capacitors are connected across that, such that power factor can be improved, because that if you operate at less power factor, then tariff charge will be higher for industrial people, because it will draw more kVA, because their tariff is sometime 2 parts, sometime 3 parts tariff, right, based on kilowatt hour, and at the same time because of the peak kVA demand. So, if that is why they connect the shunt capacitor across the suppose a motor load, such that it will draw less kVA from the network. Otherwise, for your kVA demand charge also they put they charge it. So, 3 part tariff, right. That is why you will find in industry the shunt capacitors are always there. Thank you. We will be back.